Welcome to this installment of Epidemiology of Everyday Life Lessons. In this installment, we'll talk about the relationship between two variables. This is the model that we described in our previous videos. It is the mean. I described how the mean is the value for which the sum of all of the errors of the model's predictions equals 0. And we measured the amount of uncertainty around the mean in terms of standard deviations. The standard deviation tells us how far away from our model we expect the actual values to be. Now we get to a more interesting model. We will measure how knowing some information about a person helps us improve our guess about the value of the outcome. Remember from previous videos that we call these X variables risk factors, and they helped us improve our guesses about the outcomes. For this video, we will use the example of height, like we did in the video on the Gaussian distribution. This time we will ask the question, how does height vary by sex? Let's first define what types of variables we have. Our y variable, height, is a continuous measure. Our x variable, sex, is a categorical variable. Categorical variables divide data into distinct categories. For biological sex, those categories would be female, male, and intersex. We measure the probability of categorical variables by taking the number of people classified in a category and dividing it by all of the people in the data. Put another way, the probability of a categorical variable equals the proportion of observations with that value. Every person in the world would be categorized into one of these categories. We write that constraint mathematically by writing that the sum of all the proportions must equal 1. This makes intuitive sense since we say that the chances of something happening equal the outcome we're considering over all of the outcomes that are possible. If we flip a coin, it has a probability of 0.5 of coming up heads because there are only two values, heads or tails, and the sum of 0.5 plus 0.5 equals 1. If we roll a 6-sided die, it has a probability of about 0.17, coming up with a 1 because there are 6 possible values, the numbers 1 through 6. If we multiplied 0.1666666 times 6, we would end up with 1. Categorical variables might help us also make sense of something that I said about the normal distribution, aka the Gaussian distribution. I said that the sum of the probabilities under the curve had to equal 1. These are all expressions of the law of total probability, which says that the probability of all events under consideration must equal 1. This will be something worth remembering as some of the probabilities get a little bit more complicated. For now, let's go back to our example of measuring height based on sex. One issue with the data that I use, the National Health Interview Survey, is that it requires people to answer whether they are male or female. It does not give them the option of indicating that they are intersex. This is an example of measurement error, something we will come back to in later installments. Our model will not represent the world correctly in this case, because we cannot measure intersex people, despite the fact they make up about 1% of the population. This is an example where a model is wrong in a way that is not useful. On the screen, now, you can see the distribution of heights from everyone in the National Health Interview Survey, or NHIS. It looks to follow a normal distribution relatively well, except that the right side of the graph has a longer tail than the left side of the graph. In other words, the distribution is not symmetrical around the mean. If we look at the same histogram again, but this time show the distribution of men and women, we can see why. The graph actually represents two relatively normal distributions smushed together, one for females and one for males. There are more females and they tend to be shorter, both of which reduce the mean. And a larger portion of the tallest females and shortest males are the same heights, which also pushes the overlap of those two distributions higher and pushes the overall mean lower. As a result, it makes sense for us to model these as two separate distributions, one for females and one for males. The distribution of females is shaded canary yellow, while the distribution for males is shaded light orange. You can see in the middle there's quite a bit of overlap in the distribution of heights between 64 and 70 inches. Using what we learned before, we can create a y-bar for females, which equals the mean height for females, and we can create a different y-bar for males, which equals the mean height for males. One important mathematical property links these two means. They are both constant in the data. So although each are calculated using different subsets of the data, within the overall data they have a fixed value. But now we have two y-bars, making the terminology a little confusing when we want to write one model to give us our best guess. So we use this little caret above the y and now call that value y hat. But I think that y hat should be a little bit fancier than that little caret. So we'll spruce it up a little bit in this video and give it a nice formal hat. Now, like I said, we have two means that give us information about the values of the data, y bar for females and y bar for males. But because they are constant, we can actually express them in terms of one another. Y bar for females equals the first term, while y hat for males equals the mean height of women, y bar for females, plus the difference between y bar for males and y bar for females. We can write this mathematically as y hat equals the mean of females plus the additional height of males times xi, which represents whether a person, that we call I, is male or female. If the value of x equals 0, then y hat equals the mean height of females. If x equals 1, then y hat equals the mean height of males. That is how we end up with this equation. But I want to show you what that equation means graphically so you have a better intuitive understanding of the model. And we'll cover that in the next video.